All right, welcome everyone to today's seminar. Today I'm happy to have Dr. Sean Elvidge with us. Sean is an associate professor in space environment and head of the Space Environment and Radio Engineering Group at the University of Birmingham, also known as SERENE. Dr. Elvidge's research centers on developing accurate and actionable forecasts of the upper atmosphere, which can be utilized by space weather operational centers to protect critical systems. He contributes to the UK's capabilities for space weather monitoring and prediction and advises the UK Cabinet Office and Ministry of Defence on space weather modeling and risk. Today, I'm happy to have Sean here to chat with us about inconvenient and extreme space weather impacts on the upper atmosphere. If you'd like to take it away, Sean.
That's great. Thanks very much. Thanks for the invitation. As the title said, I'm sort of going to talk about this in sort of two parts. I'm going to give some of the background on the upper atmosphere, so the ionosphere and the thermosphere, how we model that, and especially what we're doing in the UK currently, and then sort of flip tracks a little bit and talk about the more extreme space weather events and how, again, we go about estimating or modeling those. So let me start off with the upper atmosphere, the ionosphere, and the thermosphere. So, this is I think, quite a diverse group of people with lots of different interests. So I thought I'd start from sort of the basics, but at the same time also highlight where the assumptions of the basics go wrong, because very often when we talk about the upper atmosphere, especially to people perhaps up in the magnetosphere and helio sort of physics people, it gets a very simplistic picture, and that picture is something like this: is we get little wiggly line for the thermosphere, a couple of turning points as the temperature profiles change, and then we have the ionosphere, which is again just a little squiggly line that sort of sits on top of the thermosphere, and the ionosphere is really a very small fraction of the thermosphere. About 1% of the upper atmosphere is charged. So we have these two fairly simple things, and so my day-to-day job of trying to model what these two things look like should be pretty easy. If we zoom in on the thermosphere, or we think a bit about the thermosphere, which is more the focus of this talk than the ionosphere, but as they're closely coupled system, they'll accidentally flip in between a bit of both. You also get this kind of cartoon. So this is just a little curve of what the thermosphere, how it decreases sort of exponentially as you go up in altitude. And then we've got things up in space. We've got space debris, we've got satellites, the space station, Starlink, and this continues going up. I mean, this point hits zero here, but it doesn't hit zero. It just exponentially decreases up to many thousands of kilometers. Typically, what I'm interested in is probably sub 1200-ish kilometers, so low Earth orbit, where there's enough of a thermosphere component that drag is worth considering. So more we'll focus on. So if this is what the ionosphere thermosphere looked like in this very simple picture, life would be brilliant. And as I said, we wouldn't have much work to do. In reality, it's much more complicated, and it looks something more like this. We've got a whole host of different ions and neutral species, and then as well as the electron density profile, which is still sitting in here with that same shape. But on top of it, we've got all of these other components, and that's without considering neutral winds, ion winds, temperatures, all of which need to be solved for and understood if we're going to have any hope of doing any sort of meaningful modeling, understanding of the system, and then further forecasting. So that's the environment that we're sitting in. And again, even if it was like this, perhaps we could get away with it not being too complicated. But again, in reality, this is moving. So, for example, on the left here, we have winds at about 100 kilometers. And on the right, just an electron density set of profiles just going through time going forward. So they're just sort of going in day and night, and we see these sort of different parts of it sort of grow and shrink and contract, and you can see the different aspects. So we've got this mammoth number of species and winds and temperatures, and we have this very active moving system. And trying to do all of that together is sort of the main purpose of why we're trying to do upper atmosphere modeling, or what sort of the why it's not trivially easy. And all of these things are very closely related and coupled together, but we have a huge lack, really, of observations. So we have to do a lot of modeling and then some trick work to fill in the blanks. And we'll talk a bit more of that in a minute. So why does anyone care, or why does anyone bother doing this at all? So on the thermosphere side, certainly in the UK, and I know obviously broader in the US and across most space nations, there is a huge drive for a better understanding of thermospheric modeling. So whether that's for space domain awareness, SDA, or space situational awareness, SSA, we in the UK had the King launch what's called the Astra Carta, which is about essentially trying to push forward space sustainability. A key component or a key way of doing space sustainability is to understand the space environment and the thermosphere in particular. It's very hard to look at collision avoidance and space debris and space cleanup if you don't understand the natural environment. So there's a huge drive for thermospheric modeling. And that, I guess, primarily comes from this sort of slightly covered curve on the right-hand side here, which is the effective number of objects in orbit. The top line here in the sort of purpley color is in LEO, and then going down you've got MEO, GEO, and Super GEO. But I'm basically going to focus on LEO here, and you can see that from essentially the dawn of the space age, we've had this exponential growth in the number of satellites, with it really getting very steep at this point. And in LEO, so it says on this slide about 2,000 kilometers, might go a little bit under, but essentially the largest unknown in orbit determination is atmospheric drag. It's not the largest force that acts on a satellite to make it a non-Keplerian orbit. That's the gravitational field of the Earth. But we have that pretty well understood. And what we don't have a great handle on is what the drag is doing, what the density is doing, which then has this huge impact on orbit propagation, collision avoidance, re-entry prediction, lifetime estimation. And again, very simply, what that is that you have these satellites going around in orbit, they experience neutral density that has this sort of level of atmospheric drag, which then changes the orbit. In this, extreme scenario here, what happens is that then through subsequent orbits, that drag is essentially going to slow down the spacecraft, which is going to bring its orbit in until it re-enters. So that's a useful mechanism. That's some form of built-in cleanup mechanism we have of satellites re-entering. But it also means we don't always have a great understanding of where a satellite is going to be. And as that previous slide shows, there is a lot of satellites. Now, obviously, this kind of image isn't to scale, but it hopefully shows sort of a purpose. And you can pick out some. This just cutting off out here, we've got sort of the geo satellites. And depending on what size screen you're looking at, I can see it on mine, it's okay. On here, you can see these little straight lines going across it, and these are the Starlink satellites. So this is all real data. So these are real satellites that we have taken their position and propagated them forward. So this is a real look at what the environment is doing. So that's the thermosphere side. The ionospheric side, as I said, is very closely coupled. And a lot of that is then for essentially how we communicate with satellites. So one of the key, most famous, perhaps, satellites, or most historically used, are the GPS satellites, but GNSS more broadly, how we deal with position, navigation, and timing. This is a critical part of modern society. That communication link from the spacecraft down to Earth means we've got to go through the ionosphere. We've got to deal with trans-ionospheric communications. So understanding what the ionosphere does is critical. And again, from a defense perspective, it is hugely impactful, again, for radio comms. There's also a big use case, both civil and militarily, for HF communications. It's the primary means that we communicate with aircraft. And that's, there is satellite comms and there is some level of that, but it's nowhere near as used as HF communications. So that's probably essentially what this slide says. Apart from, I also didn't mention It's also critical for getting those conversion times in precise point positioning. So if you really very accurately care about where your satellite, where you are on the ground, then getting a really accurate estimate of the ionosphere is critical. And the time it takes to get to that solution essentially iterates a solution. If you have good input information from ionospheric models, you can reduce that conversion times from tens of minutes to perhaps a single minute or two. And also, as I mentioned on the HF comms, we also have amateur radio and maritime services that make use of that band. Now, long sort of median models are great for planning in this, but actually the future or what we need is real-time forecasting with a good understanding of the actual environment so we can actually develop new technology and new capabilities. So what we do in the UK, or certainly what I've been working on, is a model called ANEAS, the Advanced Ensemble Electron Density Assimilation System. It's a data assimilation model, which I'm going to talk about in a minute. So if you don't know what that is, don't worry about it. I'm going to explain it. But essentially, it is a physics-based model. So it tries to understand the underlying physics. It tries to fuse it with as many observations as we can find, and then output a nowcast and a forecast, just like a terrestrial weather forecast would, which means, like we get in terrestrial weather, we want uncertainties that do not have to be Gaussian, which if we get any time, we might talk about that a little bit, but getting past that need for Gaussian statistics to do something a little bit more interesting. With that supporting conjunction analysis, radio systems, HF communications, and radar. And again, we'll talk about how we support users in a minute. So I'm going to come back to the model, but I wanted to bring it up front so we know what we're talking about. So let me briefly talk about what data assimilation is. This is going to be about a 5-minute 101 in what DA is. So hopefully you all are where I am. Now, essentially, data assimilation is pretty easy, right? It is just an application of Bayes' theorem. We have the probability of X given Y, so the posterior distribution. So this is some probability distribution of the thing of interest, X we'll call it, given some data Y. So what is the distribution of X given a set of observations? What does the thermosphere look like given a load of satellite observations? What does the ionosphere look like given a load of HF comms? Whatever. And what we know from Bayes' theorem is that that is related to the probability of Y given X at the data distribution. So that's just the PDF of the data and multiplied by the prior distribution. So the probability distribution of our background guess. So you have some data, that's this thing. You have a background model, that's this thing. Bayes' theorem tells us how to bring them together to get this thing. And that's what we want. And that's what we do in space weather, what we do in terrestrial weather. Most space weather typically uses a variant of the Kalman filter. You might, if you know any terrestrial weather, that's maybe a little bit more varied, perhaps more variational assimilation. There are subtleties to why we do that. They all derive essentially from the same stuff. It's where you make your assumptions. But it's typically to do in space weather because we have much shorter assimilation windows, tens of minutes at most, compared to terrestrial weather where they may have like 6-hour sort of rolling windows. There's a whole host of assumptions that go into this. So Gaussian statistics, things being non-biased, things being linear, things get very computationally expensive. And there are various tricks and tips that you can do to fix that. And there are various extensions of the Kalman filter. So the extended, the ensemble, the unscented, and other sort of domains. As I said, there's variational, there's particle filters. So there's a whole host of doing it. But essentially, all you're doing is solving Bayes' theorem with these three things. So if you were to want to build your own data assimilation model, you essentially need to pick three things. The first thing you need to do is work out what background model you want to do. So we want to start with something. So here is just a set. I'm not claiming this is a complete set, but this is a reasonably complete set of empirical ionosphere and thermosphere models and physics-based ionosphere thermosphere models. As I said, they're typically coupled, the physics models. So we have a whole host of different models here. Certainly on the thermosphere side, MSIS, or the family of MSIS models from NRL. They're up to version 2, but a lot of people use NRL MSIS 2000, DTM, JB 2008. They're the real sort of thermosphere ones there. And then the physics models, WAM IPE, the model that runs operationally at SWPSI, TiGCM, WACOM-X from NCAR, SAMI3 as an NRL model. And so there's a whole host of those as well. So I want to build a new DA scheme. What do? I pick one of these. Once we've picked one of those, we need, so that's our P of X here. We're going to basically expose it to some observations. And this is just sort of a set of observations that I sort of typed up from memory. So again, this is not going to be everything there for the ionosphere or the thermosphere. And I've tried to put the ionosphere on the left-hand side and thermosphere observations on the right-hand side. So total electron content, whether that's from GNSS satellites, so that's just an integrated measure of the ionosphere. So it's a single number and it's integrated between a receiver and a satellite. That could be a ground-based receiver, or it could be a space-based receiver. But the integration along that is our most common data source tech. You get direct, or essentially in situ observations, electron density from ionosondes. And then, as I've said here, radio occultations, HF radar. On the thermosphere side, we get drag-derived mass densities and orbit-derived mass densities. So looking essentially at accelerometers on board spacecraft to estimate what the density is, or we can look over multiple orbits of a satellite, sort of know where a satellite should be, shall we say, following some orbit propagators compared to where it is, and from that infer something about the neutral density. So that's orbit-derived mass densities. We can have instruments on there specifically to help as well directly. So again, in situ observations, neutral mass spectrometers, UV remote sensing. Essentially, these are a whole set of different observations that you would like to all bring together into one coherent structure. How you actually do that can make a few challenges, because the type of observations, whether they're linear, weakly nonlinear, or strongly nonlinear, has an impact on the kind of DA technique that's appropriate for it. So back to Bayes' theorem, I've talked about this background PX, I've talked about those observations, and then the final part is just how you bring them together. What is your DA technique of, what's your favorite one to use? So for example, here, I've just got a couple on the right-hand side in yellow of different sort of techniques. So insertion or least square, so very sort of easy to throw them in. Kalman filter, the extended Kalman filter tries to deal with some of the nonlinearity. The ensemble Kalman filter, which is perhaps a bit more popular at the moment as schemes to be used. 3 or 40 variational assimilation, and a particle filter. There are others. On the left-hand side are some of those background models I talked about. There are others. But essentially, you've got those. If you join the dots together, what you get is the data assimilation models that people use. This is a reasonable set again. Now, the number of models essentially goes off, tends to infinity pretty quickly. So I sort of try to reduce the field a little bit by saying that the model essentially has to be at least 2 of these 3 things at the bottom. So either inactive development, operational, and or available for use outside of the developing institution. So it's a way of just sort of filtering out those models which appear as a one-off to do a study, which is obviously absolutely fine, but to just try and separate out while we're trying to capture which model is which. And if you particularly want to make a DA model of the upper atmosphere, what I suggest you do is pick one of these models on this side, which either has or hasn't got something next to it, and just draw a line to one of these which it doesn't already have. And suddenly you've got a new model. And there are loads of interesting things about them. So there's a whole host of upper atmosphere models. There's probably on the order of about 40. But essentially they all have some reason for existing, some unique capability. So this is just some of the DA models, so not counting just the backgrounds, but as you can see, there's a point of them, whether that's to give sovereign capability in operational environment, so operational for the US or the UK, for Canada, we've got sort of those set, and things that focus in on really specific use cases. For example, HASDM, which is really specializes in data simulation of the thermosphere. So we can learn a lot from this sort of spread of models. It tells us a lot about techniques, but also we can get at to some of the science side from different things they show us. So there's a purpose to them, is what I'm trying to sell. So that's my quick start guide into data simulation. So let me talk a little bit then about our model specifically, so Aeneas. So as I've already mentioned, the model is, slide didn't turn. Okay, so that's the thing I've already got here. So we have, this is just a map at the top right of the log of the neutral density, and at the bottom right, you can just see sort of a cut through diagram of a 3D electron density structure. So we're a full 3D model. We're making those probabilities. It's an ensemble Kalman filter, specifically something called the local ensemble transform Kalman filter, which is a way of doing all of the calculations in ensemble space. So it massively reduces the computational cost. There are other trade-offs we have to make, but it means it's sort of tractable to run in real time. And again, I'll talk about some details in a second. In terms of the data that goes into the model, we currently assimilate TEC, so total electron content, from the GNSS satellites. And we do that as a slant TEC, so the receiver either on the ground or in space, as I mentioned before. And what you're seeing in that little video in the bottom right is just the observation. So it's not model output. This is just observations of TEC looping across the day. And you can see in the really data-dense regions, like the continental US, continental Europe, you essentially you're close to not needing a model for this use case, right? Because I can see where daytime is. I can see where the slant TEC is lifting up, and you can essentially trace, you can imagine the sun in your eye. What that doesn't give me is filling in the gaps, which is pretty useful for forecasting. And it doesn't, the TEC tell me anything about the 3D structure, which is really critical for that kind of HF use case. So if you imagine down here in the bottom right, we've got, if this is the ground, and this is the vertical structure here, HF comms works by, hitting the ionosphere and bending back over. So we're sending signals up and they're going to come back down over here. The 3D structure is critical for me understanding where that ray is going to land. So it's really critical to have that 3D information. So as well as the TEC, we assimilate profiles from the ionosons, and then we can also look at the neutral density data from any essentially mission that reports it, Champ, Grace, follow on, whatever, Swarm. They are typically quite small number of those, and so we typically day-to-day only use that for validation of the model as opposed to assimilating it in. What we have been building in at the moment, though, is taking advantage of the two-line element sets. So for those of you who don't know, essentially the easy way that satellite position is reported to the community is through these two-line elements. So you make an observation, radar observations of a satellite. This is typically done by US government, but various governments are picking up themselves and commercial operators as well. But what currently happens is they make an observation, they provide you a little two-line element, 2 lines of text, which you can stick into an orbit propagator to do a reasonable estimate of where your satellite is going to be for the next 4, 6, 8 hours. And then they update the satellite position by finding it with the radar, update the TLE, and pass it back out. Now, they don't do it routinely for every single satellite every 4 hours or whatever. There are satellites which attract more often. There are satellites which attract less often. And so it's and they're using very simple technique for propagating it forward. So the satellite quickly starts to drift away from its position. However, for the satellites which are tracked reasonably well, so let's say every 4 to 6 hours you get an observation, if we run that satellite position through Aeneas, through an orbit propagator where we think it's going to be, compare it to the TLE, say, well, that difference in its position, what I'm going to say is totally down to the difference in neutral density. There are obviously other terms, the ballistic coefficient, the cross-sectional area, all these things play a role. But if I make a first order assumption that it's all because of neutral density, then I can start to infer something about the neutral density environment, and we can assimilate that information into the model. The advantage of that is that in this diagram that we had at the start, neutral density, atmospheric drag, change in orbit, that means now we can go the other way. So a change in orbit means that the satellites experience atmospheric drag, which tells me something about the neutral density. And if I can do that with all of the satellites all at once, then suddenly we've got a whole host of observations that we need to take use of. And that's great. That's a really exciting opportunity. The problem is, and obviously it's not trivial because otherwise everyone would already do it, the problem is that the two elements are a very noisy data set. So this is just an example of 3 of the elements in each panel. And this is a really sort of nice one here. It looks all smooth. You could use this quite happily. This one on the right over a long time period, but what you can see is essentially the satellite is moving down, and then there'll be a maneuver to help sort of do station keeping. So that's why it keeps jumping and falling. So these are lots of little maneuvers it's doing. You also see examples where TLEs get misidentified. So 2 objects are probably passing sort of over each other, as it were, from the radar's point of view, and the wrong satellite ID can be tagged to the wrong thing. So a lot of work has to go into filtering this out, because you don't want to derive neutral density from an object which is maneuvering. When it's not maneuvering, we'll assume it's falling back naturally, so we can infer something about neutral density. If it's maneuvering, then that would be bad, because if the algorithm tried to deal with that, it would just have to infer that there's negative neutral density, and a Kalman filter or any of these DA schemes aren't smart. They don't have a brain. They don't know that things can't be negative, and all manner of things go wrong. So if you're going to use this in our thermosphere modeling, where we're looking at about 44,000 objects at any one time, you have to be able to filter out when a maneuver is happening or not, which is what this little picture is down here, just showing an algorithm called dbScan, which we use to pull out when it is maneuvering and when it's not maneuvering, so we can assimilate that into the model. So what is the model sort of current state of affairs? So as part of a big program over the last 4 or 5 years in the UK, we've been looking at developing the Space Weather Operations Centre at the UK, based in the Met Office. And we've been operationalizing a number of models in different domains. So the ionosphere, thermosphere, radiation belt models, solar wind models, atmospheric radiation, all host of things moving into operations. Aeneas is the model that is used for the ionosphere and the thermosphere. And so that's currently running on the systems now, but the output will be available publicly for people to use from the end of this year. We're currently going through a very long testing phase, essentially, to make sure that we don't break things, or it doesn't break and it can run routinely. We run on 5-minute simulation windows, so little 5-minute chunks, and then that's updated every 15 minutes, and we also produce every 15 minutes a 24-hour forecast. The model can produce a longer forecast, and sometimes that's skillful, but sometimes that's not skillful. And that essentially comes down to the drivers of the model. We need to improve and couple in with other drivers. And that's really what our key next steps are. So I often talk about Aeneas as being a full physics model, which I sort of feel I'm justified in saying, but it's also filled with empirical models hiding in plain sight. So how do we derive the high latitude electric field? What's the lower boundary wave structure? What's the particle precipitation looks like? All of these things need pulling out. We need to be coupling into a magnetosphere model. We need to couple into a lower atmosphere wind model. There's a whole host of things that need to be done. but everything takes time. So that's the directions of travel there. And improving the data simulation as well. So we've got the physics that needs improving, but we also need to improve essentially the mathematics of how we do DA. So high latitudes is a particular challenge in the models, and we have some work looking at that at the moment. How do you generate ensembles? Now, this isn't a DA talk, otherwise we could talk about it for an hour on its own. But yeah, how do we build ensembles to do the assimilation? What's good and what's bad? And this little video on the right here is just, it's a bit jerky actually on my screen, so it probably is even worse going across the internet. But this is what I want you to just take a note at. If you look at the high latitudes, essentially, this is where the sort of interesting effects. So the colors are the temperature. This is the model lid. So this is essentially at the altitude where Navier-Stokes breaks down. So in this example, this is around 650 kilometers altitude. So that's where we can really stop modeling the atmosphere as a fluid, and we have to start moving into a ballistic regime. But what I hope you can see is that whilst it's mostly smooth, you get these weird bumps and sort of bubbles in the high latitudes. And that's why when we think about satellites and we think about space debris, high inclination orbits have this really sort of, can be really largely impacted by space weather, because it's in that regime that you get these weird sort of lumps and bumps, because that means your high inclination satellite, as it's coming over this way, experiences perhaps more density across this plane than it would if it was sort of going at a 20, 30 degree inclination. So the inclination of your satellite also really matters. It's not just, again, one size fits all. You need to have the full sort of 4D structure of the thermosphere, 3D and time, and know how it works. So that's a little bit of background on sort of modeling and what we do and the direction we're going. And now I'd like to talk about sort of a secondary thing, which is about some of space weather itself. And space weather here calling inconvenient and extreme space weather. So again, to this audience, I'm sure everyone has their own sort of idea what space weather is, but I'm going to tell you what mine is. And so the space environment itself is constantly impacting systems, technology, and health in orbit and on Earth. So we know all of that. And I think for me, space weather is those impacts, the impacts being the key part, the study of them and how to mitigate them. So operation centers maybe think of that as research to operations. Now, the extension, though, is that what is the pure research part? And that's what I think space science is. Space science is fundamental research into all and any aspects of the solar terrestrial environment. You can't do space weather without space science happening first, and they don't have to go hand in hand. You can have these people doing space science, you can have these people doing space weather. There is no hierarchical system, I think, of which is better, which is more pure. They feed each other. And then you get this sort of weird thing that people then call operations to research. So we have R2O to R, but that's essentially then space weather science, which is taking users' needs, their impacts, understanding the output from our space weather work, and how does that drive forward future research challenges. Space science challenges are tackling completely different problems generally to what space weather science is doing. They could be overlapped. There's no reason they have to not be, but they don't. They can be challenged different things, and the motivating reason behind them is different. Now, we often talk about extreme space weather, and I'm going to talk about it in a minute, but it's just worth remembering that day-to-day inconvenient space weather is really impactful. It's something that operators have to build into their day-to-day operations. So we don't have to hear about it because we build into it. Just like outside, we build in that it's going to rain day to day, but there still are floods and problems like that. But we build in certain amount of day-to-day space weather. The main one for the thermosphere, as I said, we've talked about, comes from drag. We've talked about this before, but I'm going to put in just a couple of equations so I feel like a mathematician for a minute. And essentially, what we're talking about was this estimating term here, this neutral density term when we're estimating drag. But what operators are trying to do is work out the probability of a collision. So let's say for a minute I understand where my satellite is going to be with some level of uncertainty. What they want to know is what's the probability of two satellites colliding. Now, we know we don't know exactly where it is, so we draw these ellipsoids around the satellite, which represents the uncertainty in the position. Smaller ellipsoid, more certain of a position. And then the way we determine the probability of a collision is by looking at the integral of the collision tube. So essentially, we have to propagate forward, look at where they overlap, calculate this, what's called a collision tube, and we look at the PDF in there. Now, that's great, and that gives us an estimate, but the problem is we have to start making assumptions. And one of those assumptions is that it's Gaussian. Without any evidence to say that it is Gaussian, apart from that's an easy way to work with it, and because we don't have a tool and techniques to get at that. So another thing that we can do with Aeneas is, by having this ensemble model, is look at the probabilities of neutral density, the PDFs. So this is just a single point in space. On the left, there's a latitude, longitude, and altitude I've written at the top, but this is just a single point in space. And the black sort of plus signs at the bottom are the neutral densities that the model reported, 1 point for each ensemble member. And you can see they sort of group around here, but there is some significant spread. If we use, there's a few ways you can do it. Here we use kernel density estimation, but if we bring all that together, we can provide a better estimate of what that PDF looks like. Rather than just having to fit a Gaussian onto it, we can derive a more realistic probability distribution function, which can feed in to this collision tube estimate, which helps improve to get more accurate probability collisions of a satellite, which is really useful because you'd like them to miss each other. I'm going to skip over that because I'm going to run out of time. So let me talk about then why we care about this again and why that's useful, which is essentially the number of conjunctions is increasing rapidly. And more conjunctions mean more conjunction warnings, which mean more maneuvers. But one of the critical things to remember is that most of the time, these maneuvers are unnecessary. We put large ellipsoid errors over each satellite. We're trying to be safe, that's really good, which means satellites have to move out of the way to avoid collisions. But if we can reduce those uncertainties and make fewer maneuvers, we still want to make a maneuver when it's needed, but we want to make fewer unnecessary maneuvers, which saves fuel, which prolongs satellite missions, which saves money. I mean, it's sort of an obvious scenario, but it gets harder and harder. We have a lot of satellites growing. This plot is, over a year old now, but you can see the number of conjunctions here predicted per week was growing to over 35,000 at the Starlink sort of altitudes. Now, a lot of those are very small probabilities, but nonetheless, in the 6-month period at the end of last year, the Starlink constellation made just shy of 25,000 collision avoidance maneuvers. So they were significantly large enough probability of events that we needed to move out of the way. And that's one of the things that we're looking at improving. So supporting conjunction analysis. Related to that, we talked a little bit about re-entry, or I mentioned at least in passing. So I just want to give you this one example as well, where accurate modeling of the thermosphere can help re-entry prediction. So this was the re-entry of some rocket debris, and this green track that you see here and the time above it is the potential landing area or impact area of the debris over the time period. So 4 days out, the forecast of where this is going to be was on Earth, essentially, in the inclination band that it sits in. Nothing better. 16 hours out, still close to the entire planet being covered. When we go all the way to 2 hours before re-entry, there was still uncertainty on the re-entry time of 30 minutes. So it was a 25% error on the 2-hour forecast. And what that means is that actually part of Spain here had to close its airspace briefly because they didn't know if there was a bit of rocket debris about to fall down through its airspace. Better to be safe than sorry. But this is because the density then starts to increase significantly in this area. And again, we just don't know what that is doing, and we can't really accurately model it. So again, this is an area with support with re-entry prediction. And this isn't easy. There's loads more components into it than just neutral density, but neutral density is the part that at least I can help with. Okay, so oh dear, I've gone very fast. So in my last little bit, I want to just talk about what do we mean by an extreme event. So these things I've just talked about, this is my just boring everyday space weather. This is just inconvenient stuff, right? Probability collisions, lots of them, that happens. 35,000 a week. This is day-to-day stuff. So what do we mean by extreme? Well, we could take this definition. So from NOAA's space weather scales, G5 is an extreme storm. So zooming in on that, it's threshold based. KP9, that's a G5 storm. And then there is a list here of sort of possible impacts of that system. The flip side of it is that we could define a storm by being impact based. So widespread voltage control problems, problems with satellite orientation, navigation being degraded for days, aurora, sort of latitudinal bands. Now, obviously, in a minute, I can't help myself. I'll talk about what happened a few days ago. That was a G5 storm. We hit the threshold of being at KP9. Did we see these kind of impacts across the globe? Well, I guess we still need to dig into a lot of what's happened over the last few days, but my guess is that some of these we have and some of these we haven't. And not all storms are created equal, but certainly the word extreme has a lot of sort of, it's an emotive word. So I think care needs to be taken. Right, I am going to just quickly try and explain how we model extremes, even though I'm going to have to go super fast through it. So here's a toy example just set up so I could describe it to you. Basically, here's a load of dots. It's a time series data. It doesn't really matter where it came from, but we've got a load of dots here of things moving up and down, which is stationary, so it's got a 0 mean. What I'm interested in here is what is the chance of it dropping down to minus 0.1 at some point? And we have to extrapolate. Typically with extremes, we have to do a certain level of extrapolation. And that's bad usually, but in this case, we want to. But the assumptions you make massively impact the answer. So if you pick a good assumption for your opinion, you can change the output. So in this case, if I take that data and fit a Gaussian to it, then I can just say, well, what's the chance of being less than minus 0.1? And we get 10 to the minus 20. So a pretty small value. If I zoom in on that tail and just, didn't have any data below minus 0.1, so I've just gone for a different value here. But if I go for minus 0.5, I can just count the number of times it happens and empirically get the value 2 times 10 to the minus 3. With the fit, I would get 1 times 10 to the minus 6. I've got 3 orders of magnitude different based on that assumption of what I fit. And why does it have to be a normal distribution? If I fit a Cauchy distribution, for example, I can get 18 orders of magnitude difference in the answer from a normal distribution and a Cauchy distribution. And the curve looks reasonable. There's no reason to say that one is better than that one or vice versa. The assumptions we make when fitting is really huge. So this is a quick thing just to say that there is a way to do it properly, which is what is extreme value theory. So there is a theorem, the Fisher-Tippett-Konenko theorem, which essentially says, if you want to get into the maths, these slides are going to be available so you can see it. But essentially, the limit of a probability distribution function when you're looking at extremes can only be one of 3 things. It can be a Gumbel distribution, a Fresher distribution, or a Weibull distribution. And GEV, the generalized extreme value, just brings them all together into one easy fit equation. So if you've got a big data set, meet some statistical properties, you can fit this to it and be guaranteed to have a sensible estimate of the PDF. And it's used all over the place in space weather. This is just a couple of examples of people doing it for various parameters. But it is really interesting because if we're trying to get at what is an extreme storm, then at least having an understanding of the PDF would help that answer. And again, I talked earlier how to build your own DA model with 2 easy steps. If you want to have your own EBT paper, also really easy. Just pick a thing that someone hasn't used it on before. There's loads of tools to help you do this. They're all pretty user-friendly. There's a nice, the R1 is really nice, and PyExtremes in Python is really nice. You can easily get at this kind of thing. So let me finish then with the weekend. So what is quite nice in sort of symmetry is that 2,051 years ago, astronomers in the Han Dynasty started to collect sunspot observations. That started on May 10th, 28 BC. On May 10th, we had a nice event go on. A beautiful sunspot. This was from the active region. Then here's some various data thrown at you, but we've got the big drop in DST, large KP sort of 9, and then crazy observations in the solar wind. It was a big storm, certainly the first time I've ever seen aurora in the Midlands of the UK. We have both no cloud cover and this event. It was spectacular. This is a G5 storm, as we said. So by those NOAA scales, this is extreme. So my question is it extreme? As I said, NOAA tells us it is, and it could be. But what we just need to be careful of is, are those impacts as we would expect? Certainly, it didn't show the hallmarks of some previous very big events. In terms of flaring building up to it, the largest we had was an X5.8, although that was actually just after all of the sort of main geomagnetic effects we saw on Friday night in GMT. So there were no giant flares going with it, nothing like we've seen in the other kind of Carrington Halloween storms. Typically, we know flares don't generate the big impacts, but they typically go really closely with each other. This is not one of those examples. So that's just an interesting note. In terms of satellites and satellite drag, well, I haven't had a chance to do any analysis of the environment yet, but we do know that there were impacts on Starlink. So certainly the number of reported outages increased significantly as the event started to hit. This is almost certainly not a communications problem. They communicate at quite high frequency, sort of 10, 15 gigahertz, but they do care about station keeping. So inter-satellite positioning is really important. With a change in drag, knowing where their little buddy satellite is was probably harder, which probably caused an impact on the system. The Starlink systems were really good at estimating the local density environment and correcting for it, but the impact of the storm takes a bit of time to correct for, which is probably what this is, but it will take some time looking at it. So in that case, we're not seeing that huge impact loss on satellites as perhaps would be predicted by the word extreme. In terms of the KP index, the 24-hour average was the largest, or the joint largest we ever have seen on record. The other time it got near that was in September 1941, a little cartoon from the New York Times, I think, of it. So in terms of a KP event, it was certainly very large on that scale. So let me just finish off by saying that it's really important to model the thermosphere. It's not a topic that's hugely studied, but it is really critical. Data simulation provides a great way of improving those models and making them sort of accurate and actionable going forward. And we can tackle really interesting space weather questions and really interesting space science questions. And in terms of inconvenient and extreme space weather, day-to-day space weather has an impact, and we shouldn't ever forget that. And it's really important, all the work that everybody does to understand this better. An extreme space weather event is going to have a significant impact on critical infrastructure. And I think my early take on this is that I don't think the event we've just seen is going to have that significant impact. It has impacts all over the place, but whether they are significant, that's hard to tell. Extreme is the top of the scale. G5 is the top, so we can't go bigger. So in some ways, we're telling policymakers this is the top of our scale, and we have to be careful about that. Whether it was extreme or not, it was certainly a messy event. So I'll just leave you with this little video from Matt Owens, from his model Huxley, which just models that sort of CMEs propagating through. And it's nice when you see one lift off, but to see the 6 or 7 that we saw in a row here is what made that event really crazy. And this is just such a great video, which really helped with our estimates of the arrival time as well. Right, I'm going to leave it there. Sorry, I've gone through lots and lots of things all very quickly, but I'm happy to answer any questions anyone may have. Thank you.
Awesome. Thanks, Sean, for a really cool talk. We do have a couple questions. The first is from Jason Durr regarding Bayes' theorem, closer to the beginning of the talk. His question is, I've heard that in principle, solutions can depend on sensitivity on priors. So how sensitive is the probability of X given Y dependent on slight changes in just the probability of X? Do you see that as generally quite robust, or do you see that it can cause issues?
Yeah, that is a really good question. I think I think it's surprisingly sensitive, I would say, to changes in the background model, which is a bad thing or a scary thing, actually, right? And I think it's probably one of those areas which isn't captured particularly well. I think it's one of the motivating reasons to move towards ensembles and probabilistic forecasts, because by sort of perturbing the inputs of the model, by sort of generating a spread in the ensemble, we're sort of trying to capture some of the uncertainties in PX. But it definitely has an impact. And the models which are not ensemble driven, you can see very small changes have significant changes in the DA. So yeah, I would say big, but something we try to deal with somewhat. The other way you should do it, which I don't, but I would like to, is that you can run these DA schemes with different PXs, as it were, different background models. So you should use, a bit of this model and a bit of this model, and then you get some cancellation of errors between them.
Cool. So I had a question regarding the data simulation, and you mentioned that Starlink can correct quite quickly for the change in density. Do you see a path forward to possibly including data from these very large constellations into our data simulation models to help with accuracy?
100%. So SpaceX have already shared a very large amount of data with NOAA, because it benefits them. This is one of those cases where it's going to help both parties. They provide data from the constellations. We can better improve their forecast. That's good for them. It's a great circle. The mega constellations, I'm not going to go into any sort of socio-politics of what that means. But from a data simulation point of view, these things have GPS on board and they have accelerometers on board. It provides a hitherto completely untapped resource for understanding the environment. The only caveat is they essentially all are at very, very similar altitudes, small altitude bands. And mostly that's what we've had in the past as well. Things like Champ and Grace, they all live around 450 kilometers. And we do a lot of just exponential decaying above that because we have nothing else. So it will be good in the environment that SpaceX want it, and it will be useful everywhere. But there's still some need to capture lower down, so that re-entry and the higher ups.
And higher up, yeah. So Lynn has a comment, which I will also turn into a question. He says there's a lot of red aurora, which was seen as far south in Alabama, which is rather unusual. And I like the choice of word unusual here and your choice of extreme. Unusual is things that we like to study. Extreme is decisions that policymakers might make on. But extreme is difficult because extreme often has differences for the different systems we're looking at, when something hits and where the Earth is directed, what side it's on. So extreme in terms of policy decision starts to become difficult. Do you also see a path forward? Do you think we can get to the point where we can correctly identify extreme for everyone to know so that we aren't making large decisions when something isn't going to happen?
Yeah, I mean, I think that's good. I mean, Lynn's comment is true. Certainly out of my back garden, essentially all I could see was red aurora, which, is pretty rare. But that comes from, that high activity, which, from the KP, we know it was high. But I think you're right. Unusual and extreme are key. Extreme is, in my opinion, operator specific. And I think whilst the scales are really great and have been great, they've been running since about 1999. I think that they make everything a little bit too simple. I mean, I think we have to have essentially an impact scale. I don't want to have a scale as such because you'd end up with 25 scales, but you essentially have to just have your impact per user. So if I'm a power grid person, I need to know, am I on a green, yellow, red warning today? Where I'm in Leo, am I green, yellow, red? I mean, it's different for different users. And one catch-all is dangerous, in my opinion, because if I go and speak to government people and they tell me, oh, wow, you've just told me I've had an extreme storm, but I didn't see any of these power outages you've been talking about for 20 years. And I try and explain, well, that's because this wasn't extreme enough. Danger comes. I mean, I think whatever happens, whether we go to more scales, one scale, go from G1 to 5 to G1 to 10, whatever it is, I think one of the things we need to do is probably lose the word extreme. I mean, I think this storm that we're going to look at for the months, I'm sure, and years ahead, it's the unusual properties, like Lynn mentioned and you just said, Kyle, that will be what we talk about rather than the really big, extreme, earth-shattering impacts.
Cool. Great. Thanks for the comments. I think those are really helpful. And I totally agree. I think starting to move towards specifics and taking into what we know and growing it from just this G5 could be really helpful. So that brings us to the end of a few seminars for the next little bit. We will have a short break for the long weekends coming up, and then for Gem and Cedar in June, and then we'll start up again in July with a few more thermospheric talks. So I hope to see everyone back with us in July, and thanks again, Sean, for a really cool talk. I hope everyone has a wonderful week.
Thanks very much.